Welcome to our new video series. We're testing out newer approaches to explain AI, and we need your feedback. Is it too easy? Too complex? Let us know in the comments. We love hearing your ideas for future videos as well. Please share, like, and subscribe if you find this useful. Today, we are diving deep into what we call the Agentic Blueprint, the fundamental architecture for building truly intelligent systems. We are moving beyond simple prompts and towards complex, goal-oriented AI that can manage multi-step tasks autonomously. Our journey takes us from the humble Artisan Workshop all the way to a hyper-efficient automated assembly line. This is a crucial metaphor, as it helps us understand the necessary trade-offs between systems that prioritize flexibility and those that prioritize scale and speed. Over the next few minutes, we will first break down the minimal unit of agency, explore the limits of current AI models when dealing with complexity, and then build up the two primary architectural patterns that solve these limitations: the flexible ReAct pattern and the efficient Planner-Executor Model. Understanding these blueprints is essential for anyone looking to build the next generation of intelligent software. Let us start with the core analogy that defines our architectural choices: the workshop versus the factory. These two paradigms represent the fundamental choice we make when designing an agent for a specific task. On the left, we have the artisan's workshop. Here, a single, highly skilled artisan handles every single step: measuring, cutting, assembling, and testing. This model excels when tasks require constant adaptation, when the result of one action fundamentally changes what should happen next. The process is transparent, hands-on, and deeply responsive to the environment. This mirrors the ReAct pattern, which is ideal for exploration and complex problem-solving where the path is completely unknown and requires dynamic adjustment. On the right is the automated factory. This is built around an assembly line. A foreman creates a detailed, upfront plan and then delegates specific modular steps to specialized stations or robots that work independently, often in parallel. This model dominates when we can clearly decompose the work upfront and benefit from massive scale and predictable execution. This mirrors the Planner-Executor pattern, which is perfect for maximizing efficiency, speed, and parallelization when the steps are well-defined and reliable. Before we build large factories or workshops, we must first define the most basic component, the atomic unit, which is the minimal agent loop. Agency is not just about utilizing a large language model. It is about linking that powerful model to the outside world in a continuous, self-correcting cycle. We break this loop down into three fundamental ingredients that must operate in sequence. First, we have perception. This is the agent reading the environment state. What data is currently available? What has changed? Second, we move to cognition. This is the brain where the LLM resides, deciding on the next logical action based on what it has perceived and the overall goal. And third, we have actuation. This involves the agent using tools to modify the environment, be it running a piece of code, searching the internet, or interacting with a database. This continuous loop, running perpetually within a while-true framework, is what transforms a static knowledge model into a dynamic, acting agent. It is this mechanism that enables multi-step reasoning, crucial error recovery capabilities, and the progressive refinement toward solving complex tasks that go far beyond a single prompt. Now that we understand the minimal agent loop, let us look at the fundamental limitation that necessitates its use: the limits of one-shot reasoning. When a user asks a complex query, such as, "What are the stats for the quarterbacks of the Super Bowl contenders this year?" a single, direct call to a standalone LLM often results in failure, even if the LLM is highly sophisticated. Why? Because the path to the correct, up-to-date answer is not deterministic from the initial question alone. The task cannot be solved in one cognitive step. It requires multiple, sequential, and highly interdependent steps that involve interacting with external data sources. The LLM cannot simply predict the outcome. It must act to find the information. Therefore, the task must be broken down into the necessary chain. We first need to identify which teams are the contenders, then identify the quarterback for each team, then retrieve the specific statistics for those quarterbacks using tools, and finally, format and present the results in a coherent report. This inability for the LLM to execute a full chain of reasoning and external action in a single step is the reason agentic systems exist. The first major architectural pattern we explore is the foundation of the artisan's process, introducing ReAct, which is the portmanteau for reason plus act. The ReAct pattern is the elegant solution to the problem of blind action that we just discussed. Instead of simply generating an output, the agent is trained to generate explicit reasoning traces, known as thoughts, before taking any action. This is the core concept. The agent literally thinks out loud, creating a transparent and self-correcting loop that dramatically improves performance, reliability, and most importantly, adaptability, especially in exploratory tasks. The ReAct cycle expands the minimal agent loop into 3 specific and repetitive components. First, thought. This is the internal monologue, the core of the chain of thought trace. The agent breaks down the task, reflects on previous observations, and plans the next step. Second, action. This is a concrete tool invocation that affects the external environment, such as searching a database or running a diagnostic script. And third, observation. This is the result returned from the tool, which grounds the agent in reality and allows it to correct its path if the result was unexpected or erroneous. This cycle allows the agent to navigate unknown territory, much like an artisan continually adapting their work based on the material in front of them. To truly appreciate the power of ReAct, let us trace an agent's logic through a systematic example. The query is the author of The Hunger Games younger than the author of Harry Potter? Notice how the agent systematically approaches this complex comparison, where multiple pieces of external data are required. In iteration 1, the agent's thought is to start by finding the authors of both books. The action searches specifically for the author of The Hunger Games, and the observation confirms it is Susan Collins. Iteration 2 is deductive. Now that the author is known, the thought dictates the need for her birth year to establish an age baseline. The action searches for Susan Collins' birth year, yielding the observation of August 10, 1962. Iteration 3 shifts focus, as the thought acknowledges the first set of data is complete and attention turns to the Harry Potter author. The action searches for the second author and their birth details, resulting in the observation that J.K. Rowling was born on July 31, 1965. Finally, we reach the final iteration. The thought synthesizes the 2 birth years, 1962 and 1965, correctly deducing that since 1962 is chronologically before 1965, Susan Collins is older. The action then issues a definitive finish command, providing the final, reasoned answer based on all gathered evidence. This sequential, transparent, and self-correcting method is the defining characteristic of the ReAct pattern. While ReAct is excellent for handling uncertainty, it quickly hits the artisan's bottleneck, which translates directly into a serious scaling problem in production. The core limitation of ReAct is that every single action, every single turn of the loop, requires consulting the large, highly capable, and expensive planning LLM. This is analogous to needing Tony Stark's personal, costly cognitive approval just to tighten every single bolt on an assembly line. It is grossly inefficient and slow for tasks where the necessary steps could have been clearly defined upfront. This becomes critical when we look at performance by the numbers. For a task requiring just 10 simple tool invocations, if each LLM planning call takes 2 seconds and tool execution takes 0.5 seconds, the total ReAct time balloons to approximately 27 seconds. This includes 20 seconds purely spent waiting for the LLM to think and generate the next action trace. For contrast, look at the factory process below. In the Planner-Executor Model, the initial plan might take 2 seconds, but then all 10 tools can be executed sequentially or in parallel without repeated costly LLM consultation. This drives the total time down to around 7 seconds. This massive difference illustrates the trade-off. ReAct offers unmatched adaptability, but the Planner-Executor Model offers a crucial 3 to 4 times speedup for structured tasks. If ReAct represents the hands-on artisan, then the Planner-Executor Model represents the factory floor. The fundamental insight driving this architecture is the necessity of separating the cognitive work into distinct and efficient phases. planning is inherently different from execution. Planning involves strategic, high-level reasoning about exactly what steps are needed to accomplish the entire task. This requires a powerful and expensive LLM, typically a large flagship model like GPT-4, but crucially, this powerful call happens infrequently, only once at the very start of the task. The output of the planner is the plan, a structured, executable blueprint. Execution, on the other hand, is the tactical, low-level realization of those plan steps. The executor component can use a much lighter weight LLM, or in many cases, no LLM at all, simply acting as a programmatic wrapper to sequentially call the defined tools. This makes the execution phase incredibly cheap and fast. By dedicating the powerful, expensive LLM only to the planning phase and offloading the repetitive, measurable work to specialized, lighter-weight executors, we achieve massive gains in both speed and cost efficiency, solving the scaling problem inherent in the ReAct model. The success of the Planner-Executor Model hinges entirely on the quality and structure of the blueprint, and agentic design has evolved the way these plans are structured. We start with the simplest plan, the sequential list. This is a basic checklist of steps, easy to read, but it completely lacks the expressiveness needed to define dependencies or identify opportunities for parallel execution. Next, we evolved to the variable referenced plan. Here, steps can explicitly use the output of previous steps, denoted by variable identifiers like E1. This allows for explicit data flow and better logical chaining, but it still fundamentally enforces a linear path, limiting efficiency. The ultimate blueprint is the Directed Acyclic Graph, or DAG. The DAG explicitly encodes dependencies. For example, the merge results step requires both search API A and search API B to complete first. Crucially, the DAG reveals opportunities for parallel execution, where independent steps run simultaneously. Research shows that structuring complex tasks this way can yield a dramatic 3.6 times speedup over simple sequential execution. This makes the DAG structure the definitive gold standard for achieving high throughput in factory automation blueprints. Now that we have covered the two main architectures, let us look at the fundamental components they both rely on, starting with Foundation I, the agent's tool belt. Tools are the bridge to the world. They are functions that allow agents to interact with the environment far beyond mere text generation. They transform large language models from merely knowledgeable conversationalists into capable actors that can query databases, call external web APIs, perform complex computation, and manage persistent data on the file system. Every tool that an agent uses consists of two parts: the schema, which is the JSON definition describing the tool's name, purpose, and required input parameters for the LLM to understand and utilize, and the implementation, which is the actual code that runs when the tool is called. The actual mechanism for utilizing these tools is governed by the function calling protocol, a necessary 5-step process. 1. Register tools, where the application provides the LLM with a list of available tool schemas. 2. Model decides, the LLM outputs a structured request to call a specific tool with its arguments. 3. Application executes, the agent framework runs the corresponding function. 4. Return results, the tool's output is sent back to the LLM. And 5. Model interprets, the LLM uses that result to generate its next thought or the final answer, concluding the cycle. Foundation II addresses the challenge of persistence and context depth, focusing on the JARVIS memory protocol. All sophisticated agents must solve the context window constraint. Every modern LLM has a finite context window, typically capped around 16,000 tokens in many standard applications. A long conversation, especially one filled with detailed tool call traces and lengthy observations, can quickly exhaust this limit, causing the agent to forget early parts of the interaction or previous key findings. The standard solution uses the OS analogy for memory management, separating memory into two types. Core memory, analogous to RAM, is the active context window. It is small, fast, and directly accessible by the LLM, holding the current conversation and immediate task state. Archival memory, analogous to disk, is external storage, usually a vector database, with effectively unlimited capacity. It contains the full history and long-term knowledge. The key innovation is the agent's role. The agent is given specific tools like archive memory and search memory and learns to manage this memory itself. It decides when to move information out of the active context to archival storage and when to search the archives to bring back relevant facts into active context. This dynamic management creates the essential illusion of unlimited memory for persistent, long-running tasks. Having defined both the ReAct workshop and the Planner-Executor factory, we now must consult the decision matrix, choosing the right blueprint for the job. This matrix outlines the critical trade-offs across 6 key metrics. When considering task complexity, both handle high complexity, but the factory scales better to very high levels due to its upfront decomposition. The need for adaptation is the crucial differentiator. ReAct excels when adaptation is high. The Planner-Executor performs poorly when the plan frequently needs real-time revision. Execution speed is where the factory wins, being medium to fast, while ReAct is fundamentally slow due to its cognitive overhead on every loop. This speed difference directly impacts cost efficiency. ReAct is low efficiency, whereas Planner-Executor is high to very high efficiency because it minimizes expensive LLM calls. For parallel execution, ReAct offers none, but the factory is highly capable, especially when utilizing DAG plans. Finally, error recovery is excellent in ReAct because the agent self-corrects on every step, while the factory's reliance on an upfront plan makes its recovery only fair. Therefore, choose ReAct when the task is inherently exploratory, actions significantly inform the next step, and maximum transparency into the reasoning process is required. Conversely, choose Planner-Executor when the task is easily decomposed upfront, and speed and cost efficiency are the critical metrics for success. Building agents for deployment is not without its risks, and in production realities, even the best blueprints sometimes fail. We must anticipate and safeguard against common failure patterns. The first major pattern is infinite loops, where an agent gets stuck repeating the same failed thought and action cycle indefinitely, perhaps retriggering a tool call that will never succeed. The safeguards here are mandatory. Implement max iteration limits, which provides a hard stop after a predefined number of steps, and loop detection, which halts the process immediately if the agent repeats the exact same action sequence multiple times. The second common failure is context pollution. This occurs when irrelevant information from early tool observations or unrelated parts of the conversation degrades the overall performance and distracts the agent during later, crucial reasoning steps. The safeguard is context pruning strategies, such as automated summarization of long logs or importance-based removal of low-priority information from the active window. The final pattern is tool misuse, where the LLM calls a tool with the wrong arguments, such as passing a string where an integer is expected, or calls it at an inappropriate time. We safeguard against this by providing extremely clear tool descriptions in the schema and using validation layers in the framework that reject any malformed calls before they are ever executed by the underlying infrastructure. We have referenced the agent's internal monologue several times. This crucial function is powered by the cognitive engine, the spark of chain of thought, or COTI. What exactly is COTI? It is the simple, yet profound, act of prompting a model to show its reasoning steps before giving a final answer. The now famous trigger phrase, "let's think step by step," is often all that is needed to unlock this capability in modern LLMs. Why does it work so effectively? By verbalizing its reasoning process, the model is compelled to focus its attention, creating intermediate anchor points for its logic. This significantly reduces the chance of silent calculation errors and dramatically improves the logical consistency and accuracy of the output. It is widely considered an emergent ability of large-scale models. The connection to agents is fundamental. The thought step in the ReAct cycle is not just any text generation. It is a chain of thought trace. COTI is not a separate technique from agents, but rather the cognitive substrate that makes effective agentic systems possible. It allows the agent to monitor its own thinking, catch errors early in the cycle, and dynamically adapt its plan, justifying the name reason plus act. We conclude our look at the Agentic Blueprint with the final takeaway on the art of agentic design. We started this journey with the minimal agent loop, the atomic unit of perception, cognition, and actuation. We then iteratively added crucial elaborations, each designed to solve a specific problem with the previous, simpler layer. We introduced ReAct for robust adaptability and self-correction. We added planning for efficiency and necessary scale. We integrated tools for external action and bridging to the outside world. And finally, we implemented memory for persistence and overcoming the context window constraint. The art of building effective agents is not about rigidly memorizing a fixed set of patterns. It lies in truly understanding these architectural trade-offs, knowing the common failure modes, and choosing the right combination of elaborations for the specific job at hand. When you approach a new task, always remember this powerful design mantra. Start simple. Identify the break. Add the fix. Iterate. Thank you for joining us for this deep dive into architecting intelligent systems.